This is Lab 1 Constant Velocity by Samantha Hefner and Physics 2211 at Georgia Tech. So the purpose of this lab is to observe Newton's second law in the real world. We're going to verify its accuracy and view how realistic it is for an object to move at a constant velocity in the same direction with no outside forces on it. We'll see that even though it is possible for an object to move at a near constant velocity for a short period of time, it's not sustainable and there are almost always outside forces that will change the motion of the object. This lab uses data from the real world calculated with tracker and computational models, which we're going to create with code, to compare predicted to real world results. And then we're going to compare them by graphing both results in a position versus time scatter plot graph. So the main fundamental physics principle is Newton's second law, specifically that an object with no forces acting upon it or all the forces acting upon it cancel out to zero, then that object will experience no acceleration and its velocity will remain constant. So we're going to show this using the velocity update formula, which is that the final velocity equals the initial velocity plus the net force divided by mass times delta t. So if the net force equals zero, then we can work the formula around to show that the final velocity is going to equal the initial velocity. So the second formula we'll use is the position update formula. The final position equals the initial position plus average velocity times delta t. And because there's a net force of zero, the average velocity is going to equal the final velocity, and we showed above that the final velocity equals the initial velocity. So we can then use the average velocity formula, which is change in position over change of time, to calculate the initial velocity. And then, so the final velocity equals the initial position, plus initial velocity times delta t. So this is a model. I used a tennis ball as my object, and the tennis ball is going to be my system, and I rolled it across a table, and the surroundings are going to be the table and the air around it. Because we're assuming that the net force is zero, we're going to assume that friction and air resistance are negligible. So the only forces are the force of gravity and the force of the normal force, and those cancel out. So my initial conditions are that I'm going to roll a tennis ball along a smooth, long table with no ridges in it so that it will roll across at a constant velocity. So I recorded it and analyzed it with tracker, and then I made a position versus time graph, and then I compared that graph to a position time graph I made using GlowScript. So here's the tennis ball. And then this is what it looks like when I analyze it with tracker. So the X position is the position we're looking at here, and this is the graphic created. Okay, so for my code, I calculated the initial velocity, which I talked about earlier, using the average velocity formula, and then I got 3.3645, so I put that into my initial conditions, and then I changed the time to last for 0.310 seconds, which is how long the tennis ball rolled across the table. And then for the velocity, I put in the velocity update formula, and then for the position, I put in the position update formula. And then put that all into Excel, and this is the graph I made. Okay, so the orange is the predicted, the blue is the observed, and these two lines are very similar, but they are a little bit different. The observed data has a slight curvature due to the circumstances of the surroundings not being perfect. So we are going to see a bit of a frictional force act on the tennis ball, making it slow down a bit. The velocity is going to slow down or change, and we're going to see a slight downward concavity in the graph. The computational model shows a perfect linear slope of the object moving at a constant velocity, or Newton's second law shows a net force of zero, and that's what that graph looks like. So the observed model does not have a perfect linear slope, so there is some unaccounted for force acting on the object or the tennis ball, so that the net force is not zero and there is an acceleration as shown by Newton's second law. Okay, so when you analyze your video, what if the positive x and the negative x were interchanged? So this would cause a downward sloping graph starting at the origin and sloping down into the negative numbers. However, the magnitude would stay the same because we're not changing the actual data, we're just changing the axes. So it is possible to make an assumption about the number of forces that should add together to create a net force of zero, because this is a fairly simple system, just a tennis ball rolling across a table. So there's always going to be a normal force, and there's always going to be a gravitational force, and those cancel out. So that'll be a net force of zero. And the force of any push on the ball, making the ball move, should cancel out with any frictional or drag resistance that's going to push in the opposite direction of the push. So that would be 4 or 5. Okay, so conclusion, we observed the motion of an object moving at a constant velocity, and then we compared that to real world results to a computational model of the object using GlowScript, and we saw that there was a bit of a force acting on the tennis ball, making it not a perfect constant velocity.